about exact time evolution by sampling random circuits.
Hi, hello everyone. I'm Chusei Kiumi from a Center for Quantum Information and Quantum Biology at the University of Osaka. And today I'm excited to talk about our new algorithm proposal, which is called TE-PAI, which simulates the time evolution exactly by sampling the random circuits. This work is a joint work with Balin Koptel from University of Oxford. First, I will quickly discuss about the background and the motivation. Now we have a noisy intermediate scale quantum computers, which does not implement quantum error corrections, which suffers from the noise. But we are gradually transitioning to an early FTQC eras. And so it is very important to design a quantum algorithm that which is resource efficient and also offers theoretical guarantees for the performance. And our main motivation of the research is to accelerate the realization of the practical quantum advantage. And the main idea of the research is that to consider a hybrid classical quantum strategy to make the existing quantum algorithm more resource efficient. So to make the quantum algorithm, the existing quantum algorithm has large quantum resource requirements, then we add more classical processing to reduce the complexity of the classical of the quantum computations. Here, the quantum resources mean a lot of things in a different context. But here, we focus more on number of qubits, circuit number of quantum gates, number of resource states like T states, and gate fidelity, and so on. As everybody here knows that the Hamiltonian simulation is one of the most important applications of the quantum computers. And Hamiltonian simulation is a key candidate for demonstrating a practical quantum advantage. So first, the quantum system is governed by the Schrödinger equations, and the Schrödinger equation has this Hamiltonian, governed by this Hamiltonian. In this talk, we'll focus on time-dependent Hamiltonian, which has the time-dependent coefficients with Hamiltonian terms. Here, without loss of generality, I'll assume this coefficient to be a positive and integrable over time. And then the time evolution operator is defined as follows. And what we want to solve is that we want to estimate expectation values of the given observable O. And there are several quantum algorithms that that solves this kind of problem. Like the variation quantum algorithm, like VQEs, has a very low overhead and it's very easy to implement on the current hardware, but it has poor theoretical guarantees for the practical quantum advantage. On the other hand, we also have more sophisticated quantum algorithms, such as linear combination of unitaries and quantum Seeger-Valley transformations. It has better computational complexity, that's better scaling, but it is very hard to implement for the current noisy devices. So in this research, we're focused on this trotterizations, which has simple implementation and low overhead, and it still has the theoretical guarantees for the performance. And it often outperforms than the theoretical expectations. So I believe this trotterization is a very practical algorithm for the demonstration of practical quantum advantage. And the trotterization is basically a discretization of the time evolution operators. So we divide the time evolution operators into small pieces, and each pieces we consider operating this Pauli rotation angle. And so due to the discretizations, we have the so-called trotter errors. To reduce these errors, we need many time steps, which is called the trotter steps. And based on this trotterization, we kind of develop more low overhead, like a more resource efficient quantum algorithm called TE-PAI. So this is the overview of our algorithm. So in the left, we have the trotter circuits, and on the right, we have the TE-PAI random circuits. The trotter circuits has a continuous angles rotation gates. But on the other hand, our circuit has shallow circuits with a fixed angles rotation gates, which is just delta and pi rotations. But we need more samplings. So to get a good estimation of the expected number, expectation values, we need more samples in TE-PAI. And it's magnified by this factor called a gamma factor G. But the big advantage of our algorithm is that when we want to reduce the trotter errors in trotter circuits, we need infinitely deep circuits to make the errors to be zero. But our algorithm, even we consider an infinitely deep, infinitely large number of trotter steps, we still have a finite expected number of quantum gates and sampling overhead. And also, the advantage is one more advantage is that we can kind of choose the delta rotation angles by ourselves. Then we can control the trade-off between the gate counts and the gamma factors, the sampling overhead. And before going into detail to our protocol, we quickly review the quasi-probability decomposition, which is a basis of our algorithm. So this is to decompose the quantum channels. So we consider a quantum channels corresponding to this rotation gates into a linear combination of easier rotation angles. So one is the identity channels, which basically do nothing. And then the second one is the delta rotations, and third is the pi rotation. And we also define the probability distributions as weights of each coefficients, absolute value of each coefficients. And we also note that this has the analytical expressions. So we know these values before we run the algorithm. And the previous research states that if we randomly replace these rotation channels to one of each rotation channels, we get the unbiased estimate of the original quantum channels by multiply by this gamma factors. So we use this method into trotterization circuits. So the protocol is that we have input, which is the Hamiltonian time-dependent Hamiltonian H, and simulation time T, and observable O. And what we want to output is the estimation of the expectation values of O. And for step one, we generate a random circuit based on the protocol that I just defined in the last slide. And then step two, measure the random circuit and then multiply by the prefactors. And then at the end, we just repeat this process multiple times and output the mean values to get an estimation of the desired result. So as a step one, first we set the trotter step N, and then generate a trotter circuit, and then randomly replace the rotation angles based on the PAI, the method that I introduced in the previous slide, to make shallower quantum circuits, which only has fixed delta and pi rotation angles. And then we multiply by the prefactors. So we get the result. We can measure from this random circuits and get the result of m hat, which is either plus minus 1. And then we multiply by this gamma factors and sign factors. So this sign factors means that if you select the quantum gates, the rotation gates has the negative coefficient, then you flip the sign. And then we get the result O hat. And then we repeat multiple times to run this circuit and measure, correct the results from the random circuits. And as the quasi-probability decompositions, the PAI method shows that this is an unbiased estimator of the desired result O hat, the expectation value of O. So we can just compute the mean values of this output to get a desired result. But the measurement output is magnified by these gamma factors. So we need more samplings to get a better precision. So this is kind of a trade-off between the simplicity and the sampling overhead. And the main result of our algorithm is that even we consider n goes infinity, the expected number of quantum gates converges to some constant values. So this figure shows that if even we consider large n, the quantum gates count won't increase asymptotically. And this gate count is linear to the simulation time t, and it's L1 norm dependence defined by this. And because we are dealing with a random circuit, so each circuit has different number of quantum gates, and this is the probability distributions of the gate counts, and it can be approximated by normal distributions. Also, the sampling overhead also converges. But in this case, the sampling overhead grows exponentially as the simulation time t and this L1 norm. So this is a big downside of the TE-PAI algorithm. But we can kind of control this sampling overhead by controlling the value delta. So this delta can be chosen from 0 to pi because we're considering small theta, so we can kind of think this as like 0. And if you want to suppress the sampling overhead, we can just choose small delta. At the cost of increasing number of gate counts, we have suppressions for the sampling, or the exponential suppressions for the sampling overhead. So I won't go into detail about this slide, but I also want to emphasize that only non-Clifford operations that we need to implement this algorithm in the fault tolerant architecture is only the non-Clifford gate required is the delta rotations. So if we can efficiently prepare the multiple copies of delta resource states, then we can significantly reduce the fault tolerant implementation cost. So in the paper, we also propose methods to kind of efficiently prepare this delta resource states, combining the repeat until success method and catalyst tower method, recently proposed by Sun. So let's get into the concrete example. As a demonstration purpose, I've set the target Hamiltonian as this Heisenberg spin Hamiltonian, which has the highly oscillated term in the second term. And as observable, we choose x0. And this figure clearly shows the advantage of the TE-PAI for this specific Hamiltonian. The gray one is the deep shorter circuit, and the blue TE-PAI distribution correctly estimates the expectation values with just a small number of quantum gates. On the other hand, the slightly more quantum gates, the shallower shorter circuits suffers from this shorter errors, but the downside of TE-PAI is that this growth of the statistical errors. This is a snapshot of the time evolutions. So TE-PAI is good that it's correctly following the correct result, but the variance grows exponentially as simulation time t grows. So as a summary, we developed a TE-PAI algorithm which simulates average time evolution without discretization errors with finite circuit depths and sampling overhead. And the circuit is very simple and shallow, consists of only delta and pi rotation gates, which makes it compatible with many kind of techniques like classical shadows, like spectroscopies and many kinds of error mitigations. It also allows for a highly configurable trade-off between a circuit depth and measurement overhead. So this delta value can be chosen by the user's preference. So this algorithm is very flexible in terms of the trade-off, cost trade-off too. So this is end of the talk. Thanks for listening.
I think Alex has a question.